Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence and robotics research. Today we're examining 8 groundbreaking papers from Computer Science Robotics, all published on August 31st, 2025. These papers showcase remarkable advances where mathematical precision meets human unpredictability, from surgical robots requiring billionth of a second accuracy to autonomous vehicles navigating through unpredictable human drivers. We're witnessing the development of tomorrow's collaborative robot partners that can seamlessly integrate into our complex, dynamic world. Picture this scenario. A surgical robot performing a delicate heart operation suddenly freezes mid-procedure because it can't solve a simple trigonometric equation fast enough. Meanwhile, across town, an autonomous vehicle swerves dangerously because it can't predict how the aggressive driver in the next lane will behave. These scenarios might sound like science fiction gone wrong, but they represent very real challenges that robotics researchers face every single day. The difference between a robot that works flawlessly and one that fails catastrophically often comes down to mathematical precision measured in billionths of seconds and algorithms that can predict human behavior with uncanny accuracy. What makes today's research particularly exciting is how these scientists are solving problems that have puzzled the robotics community for decades. Computer Science Robotics sits at the fascinating intersection of pure mathematics, computer science, and real-world engineering challenges. Think of it like being the architect of a digital brain that must control a physical body. Just as our human brains seamlessly coordinate complex movements while processing sensory information and making split-second decisions, robotics researchers must create computational systems that can perceive, reason, plan, and act in the world around them. This field encompasses everything from the mathematical foundations that solve inverse kinematics problems in robotic arms, to the sophisticated algorithms that enable autonomous vehicles to navigate safely through busy city streets. It's literally the brain behind the brawn, transforming mechanical systems into intelligent agents capable of performing complex tasks. What makes computer science robotics particularly captivating is its interdisciplinary nature. Imagine a melting pot where control theory meets machine learning, where computer vision dances with optimization theory, and where even game theory finds its way into solving real-world robotics challenges. The papers we'll examine today showcase this beautiful diversity, presenting solutions that range from pure mathematical approaches that could have been written by ancient Greek geometricians to hybrid systems that combine multiple computational paradigms in ways that would have seemed impossible just a few years ago. The importance of this field extends far beyond academic curiosity. When you ride in an elevator, use a smartphone, or receive a package delivered by drone, you're experiencing the practical results of computer science robotics research. The first major theme emerging from today's research focuses on mathematical foundations and algorithmic robustness. Think of this as building the perfect foundation for a skyscraper. You can have the most beautiful architecture in the world, but if your foundation isn't solid, the entire structure will eventually collapse. In robotics, this foundation consists of numerically stable methods for solving fundamental problems. We see this clearly in groundbreaking work on trigonometric equation solving for robotic kinematics, where researchers have developed methods that achieve machine precision accuracy with 100% success rates. This includes revolutionary advances in inverse kinematics using computer algebra systems and comprehensive Grobner systems. These mathematical foundations are crucial because they form the bedrock upon which all higher-level robotics applications are built. The second prominent theme centers on motion planning and trajectory optimization. Imagine trying to navigate through a crowded marketplace while carrying a tray of delicate glassware. You need to move efficiently toward your destination while avoiding obstacles, maintaining smooth motion to protect the glassware, and adapting to unexpected changes in the crowd. This is essentially what robots face every day, whether they're manufacturing automobiles or serving coffee at a busy cafe. The papers showcase various approaches, from model predictive path integral methods that leverage configuration space-distance fields to comprehensive path planning frameworks that optimize entire trajectories for 6-degree of freedom manipulators. Remarkably, these systems are achieving control frequencies exceeding 750 Hz while maintaining nearly 100% success rates in complex manipulation tasks. The third theme focuses on autonomous vehicle decision-making and multi-agent systems. This research addresses how autonomous vehicles can make intelligent decisions in complex traffic scenarios, involving multiple human drivers with different behavioral patterns. Picture a chess game, where half the pieces follow the rules you expect, but the other half belong to players with completely different playing styles, some aggressive, some conservative, some completely unpredictable. The work on mean field games for interactive decision-making represents a sophisticated approach to modeling and predicting the behavior of multiple agents in dynamic environments. These systems have achieved zero collisions across multiple challenging scenarios, while successfully bridging psychology and mathematical optimization through quantitative mapping of behavioral traits to specific driving parameters. Today's research presents several groundbreaking results that have significant implications for robotics. One of the most remarkable findings relates to numerical stability in fundamental robotics computations. Research on solving trigonometric equations in robotic kinematics has achieved machine precision accuracy with less than 10 to the negative 15th power error and a 100% success rate. To put this in perspective, this level of precision is like measuring the distance to the moon with an error smaller than the width of a human hair. Another breakthrough involves real-time optimization at frequencies exceeding 750 Hz while maintaining optimal performance. Zero-collision autonomous vehicle decision-making has been demonstrated across challenging traffic scenarios. Photorealistic mapping in dynamic environments now operates in real time, and risk-aware planning systems simultaneously optimize safety, efficiency, and comfort. Let me take you deeper into one paper that truly exemplifies the cutting-edge nature of this research. Young and colleagues have presented groundbreaking work that addresses one of the most challenging problems in autonomous vehicle research: how to make intelligent decisions in traffic scenarios involving multiple human drivers with wildly diverse behavioral patterns. What happens when an autonomous vehicle programmed to follow traffic rules perfectly encounters a driver who treats speed limits as mere suggestions? These scenarios represent the daily reality that autonomous vehicles will face. The researchers' approach centers on mean field game theory, providing an elegant solution to overwhelming computational complexity. Instead of tracking individual interactions between every pair of vehicles, each vehicle interacts with a mean field that represents the aggregate behavior of everyone else, extended to handle human behavioral diversity through quantitative mapping of abstract traits to concrete parameters. The technical breakthrough lies in mean field theory's elegant solution to computational complexity. Rather than tracking every possible interaction between drivers, which would be computationally overwhelming, each vehicle interacts with an aggregate behavior field representing everyone else's collective influence. This framework has been extended to handle beautiful human behavioral diversity through sophisticated mathematical modeling. Picture a spatial influence field model where aggressive drivers have larger influence radiuses, like storm systems affecting weather patterns far from their center, while conservative drivers have smaller but more intense influence on immediately adjacent vehicles, like lighthouses providing strong guidance to nearby ships. Dynamic safety margins adjust based on current traffic conditions and behavioral profiles of nearby vehicles, with time-to-collision analysis providing real-time conflict assessment. What makes this work particularly compelling is its philosophical approach to human-machine interaction. Instead of trying to make humans behave more like machines, or treating human unpredictability as a problem to be solved, this research embraces human behavioral diversity as a feature to be understood and accommodated. The experimental validation tells an impressive story: zero collisions across 6 different style combinations and multiple complex scenarios, while consistently outperforming conventional game theoretic baselines. The implications extend far beyond autonomous vehicles to warehouse robots working alongside human employees, service robots in retail environments, or even drone swarms navigating around unpredictable bird flocks. The safety-critical decision-making framework provides a template for ensuring safe operation in any robotics domain where failure could have serious consequences, bridging abstract mathematical theory with deeply human concerns about safety and comfort. Looking toward the future, these research directions paint an exciting picture of what's possible in robotics. Think of the current state of robotics research as standing at the base of a mountain range, with each peak representing a different challenge we're working to overcome. The convergence of multiple research themes suggests we're approaching a tipping point where robots will transition from being sophisticated tools to becoming true collaborative partners. The mathematical foundations being laid today will enable robots that are not just precise and efficient, but also adaptable, safe, and intuitive to work with. Advances in real-time perception and dynamic environment handling point toward a future where robots operate seamlessly in the messy, unpredictable real world. Picture service robots in hospitals that can navigate crowded corridors filled with patients, staff, and equipment, adapting their behavior based on mission urgency and human needs. Autonomous vehicles might improve overall traffic experience for everyone. And democratized access to robotic assistance could provide personal robots that truly adapt to individual preferences. Today's journey through the frontiers of computer science robotics has revealed a field simultaneously tackling fundamental mathematical challenges and addressing deeply practical human needs. From achieving machine precision accuracy in trigonometric computations to modeling the beautiful complexity of human behavioral diversity, these researchers are building the foundation for a future where robots are not just tools but partners in creating a better world. The 8 papers we've explored represent more than academic achievements. They're stepping stones toward a future where the boundary between human and artificial intelligence becomes increasingly collaborative rather than competitive. Whether ensuring surgical robots never make precision errors, enabling autonomous vehicles to navigate safely among unpredictable human drivers, or creating service robots that work naturally in dynamic human environments, this research is shaping the world we'll all inhabit. This research synthesis was created using advanced AI systems to bring you the latest breakthroughs in accessible format. AI synthesis was performed using Claude Sonnet 4 from Anthropic, with TTS synthesis powered by Deepgram technology and image generation through OpenAI systems. Human expert review was conducted on all synthesized content to ensure accuracy and clarity. We acknowledge that potential oversights may exist, and detailed references are provided for those who wish to explore the original research papers. This process represents our commitment to making cutting-edge research accessible while maintaining scientific rigor and acknowledging the collaborative nature of modern content creation between human expertise and artificial intelligence systems. Thank you for joining us on AI Frontiers today. I encourage you to dig deeper into these papers yourself and share your thoughts about this research on social media using the hashtag AI Frontiers. Subscribe to our channel for weekly deep dives into breakthrough research and community discussions on emerging technologies. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive preprint server.